Here's another video looking at you. In this video we're going to take a look at converting this 36 volt 550 watt solar panel into three 12 volt panels in the individual panel. Let's take a look at the connection. So we can see we have the two MC connector with the wire, and this is the specification. So we can see with an open circuit it's approximately 51 volts, and on that working circuit, which is the maximum power voltage, is 42 volts. So this will be able to connect to a 42 volt or 36 volt charger on an MPPT, not a pulse width modulator. If you're going to connect this panel to a pulse width modulator, it will have to be connected to a 42 volt charge controller with 42 volts battery. Now let's take a look at the reverse side of this panel to see what it looks like. It's not your conventional panel from the rear. This is the reverse side of that panel, and when we take a look at this wire where it's connected to, this will most likely be the positive, and on the other side here will be the negative. But what I've done, I've dug out this silicone from the ports. It used to be like that, and we got it like that. So we could see in there, that's a Schottky diode, and that's another one right there. And most likely you see the impression on the outside of that silicone gel of it. So that's what the back of the panel looks like with those three connectors. What I'm assuming is maybe we have to test these here to see what voltage we get, and over here and over here. So common sense is telling me that since this is a 36 volt panel and the sticker says 42, I'm expecting anywhere between 12 to 20 volts at these ports, if possible. If that is possible, what we're doing here is we're segregating this one panel into three, and that will probably be approximately 175 watts at 12 volts, because 175 times 3 comes out somewhere around 500. You could work out the exact number if you're into that kind of stuff. So that's the idea here. Most of the time you will have a junction box up here, a big box with a diode in it and the two wires that comes out on this panel up there. And there's already a video showing you how to get that panel into 12 volt by dissecting this canvas, this white plastic, and exposing this connection on the cell in the solar panel. So our next step is to take a volt test on these connectors with the panel in the sun and where it currently is to see the results. When looking at the front of the panel, the face, this is what made me, or will make anyone, think that this panel could be segregated. When we take a look at the connection here, you could see these connectors, these circuit board, are going to the back of the panel. Here's another one here. So you can see they're separating protruding the panel going to the rear. And that is what you should look for to know if the panel could be converted or segregated for more or lesser volt to satisfy your pulse width modulator charger. Now, if you have an MPPT charger, you would not have to do this because the charger will be able to figure out all the specs of the panel and produce the correct voltage amperage for your charging system. But for a pulse width modulator, you need to match the charger volt with the battery and the panel. It does not matter if it's a 12 volt system, 24 volt system, 36 volt system, 42 volt system. All the component voltage must match, but the wattage could be whatever it wants to be. The voltage is what's important when setting up pulse width modulator solar charging circuit. Back to the rear of the panel. Voltage has been checked at all these connectors and have been specified. This side is a positive and the other side is a negative. Same thing over here and over here. With a voltage test from these two pins, with the panel in the sun, middle of the day, bright sunlight, approximately 20 to 21 volt on this connector. This one was 10 volts at maximum sunlight with no cloud, and this one was 20 volts, equal to this one over here. So what we have established in this panel is that we have two panels inside of the panel that are 12 volts that could work to 12 volts. Those are the 20 volts port, the two outer ones. And the middle one is a 10 volt, which is most likely not going to be useful for us. But we are going to wire all these wires, which are going to be 6 of them, parallel into the charge controller to see what maximum voltage we will receive on a bright sunshine day with no cloud. If the 50 amp 12 volt charger will be able to handle the voltage, which will most likely reach a maximum of 17 to 18 volts. That's because there's a load on the circuit. With an open circuit, the voltage will be higher, like I established, 20 to 21 on the two outer ports. Once they're connected, they will be compressed into amps and most likely idle around 17 or 18 volts, 16 around there. All depends on the performance of the panel and the radiant sunlight. The middle one, same thing applied. It's between 8 to 10 volts. Once this panel is wired in to the charge controller parallel, which means all the positive comes together and all the negative comes together, and they go into the charge controller positive and negative. No series connection. We will see approximately 20 volt as a maximum on the charging, but it's not really 20 volt if you can understand. The circuit is parallel. You have two 20 volts and a 10 volt, which you're not going to be able to see on the charge controller because it's wired in parallel. But what you're going to be able to see is amperage. The amperage is going to be way up than your normal 20 volt panel. This is 2.5 20 volt panel you have connected together that the charge controller will be able to see, but it will not be able to display it. The only way it'll be able to see it is through the amperage. Once you look at the amperage display, you're going to see the amperage is actually 2.5 times more what a normal 20 volt panel will have. So since this is a 500 watt, I'm assuming one side of the panel is 200 watt and the other side is 200 watt. That's the ones with the 20 volts, and the one with the 10 volt is probably 100 watt. So we're going to get 400 watts out of the panel if we decide to connect just the 12, the two outer ports for performance. But don't forget, you could also wire in that 10 volt, which will also be additional to your 220 volts that you have wired into the charge controller. What you're doing is you're increasing the amperage, but keeping the voltage the same in a parallel circuit. You need to study it. You'll get it as we go through the video. It's now early in the morning. I have the solar panel on the back of the pickup truck. You can see all the wires coming down into this voltmeter, and we're currently reading approximately 9 volts. To prove that it's real electricity that we are receiving from the panel, this is from the center connection, which is approximately 10 volt. We are lighting a 12 volt automotive filament light bulb with it. So this is not an LED light bulb. This bulb really takes energy, true energy from the circuit. So this is letting us know that this circuit has energy. Now it's time for us to test the ones on the side, which are 12 to 21 volts. Okay, so here we could see we have the 12 volt connected, and it's showing more than 16 volts. You see the needle right here past 16 volts. So that's approximately 20 volts. I'm pretty sure if we use that bulb, it's gonna burn. Okay, so the bulb is a lot more brighter with this circuit, which will be the same thing for the other side. Now we have the battery, the charge controller connected to the center connection 2 wire, and those 2 wire were reading a maximum of 10 volt. You see it comes down there, goes into that spool, and then it goes into the charge controller. Now let's take a look at the reading on the charge controller. So that flickering is caused by the camera. We're charging at close to 13 amps. And battery volt is 11.7. Panel volt is 12.2. And we're charging at 16.4 amp. Now I want to use another charge controller just to verify what we're seeing is actually taking place. Here is a 12 volt 50 amps hour battery connected to the pulse width modulator charge controller. You can take a look at the wires, see how they go in there, and this set of wire right here goes to the right side 12-20 volt panel. And let's see what we're getting right now on the charge controller. It's showing it's charging from the sun to the battery. 13.5 volts on the battery. Now that flickering is caused by the camera. 3.8 volt early in the morning. So this is 200 watts at 12 volt, giving us 3.8 amps. Currently 600 watts inside the house is giving us approximately 12 amps. So as the sun rises, this amperage is going to increase. This is the same charge controller that was used on the panel complete when it was in series. That's by tying the 2 ends together into the charge controller. We receive a maximum of 10 amps with all the panel in series at 36 volts, 500 watt. So we could see we're already getting almost a half of that early in the morning. As the sun rises in the middle of the day, we're going to take another look at this charge controller to see what amperage 200 watts at 12 volt is giving us. Remember, we have another 200 watt at 12 volt panel in the same board, and then we have that 10 volt. So we're going to make connection to all of that as the sun hits in the middle of the day. Currently It's right above the trees. This light bulb is connected to the battery because I want to create a drain in the battery to see what's the maximum amperage this charge controller could charge or extract from the panel. So currently the panel has been disconnected from the charge controller to allow the bulb to drain the battery. Now here's the issue that we're having. With one side of the 12-volt panel connected to this charger and the other side, which would be these two wires, connected to this charge controller on the same battery, we're experiencing a night mode. That light will come on when we try to connect both sides of the 12-volt panel to different chargers. If we try to connect both sides of the panel to one charger, we will still get that night light. So that light goes away once I put this back on in place. You see it goes away. Let's just check, see the amperage it's currently charging at. It's now 9 in the morning and we're charging at approximately 6.3 amp. So we're going to let the battery drain some more so we could see at midday what's the maximum amperage on one side of this solar panel. We can see the battery is charging from the drain of the light bulb, and the amp now is 11. Okay, we almost saw 12 amps. This is more than we were seeing when the panel was connected with the two wires in the back at 32 volts, and it's approximately 9:30. I also have this bulb here connected to the end of the panel for this side. So we can see we're getting a voltage here, but if I connect these wires into these points right here, parallel with this wire, the night light comes on the charger. So this has something to do with the battery and the panel still in series. We have to go up into that area there and maybe remove that plug, and we're gonna have to make some connection. You could see these connectors, these strips running on the white lead. We're gonna have to connect those bus bar so we could have two 12-volt panel or three 12-volt panel. So right now the sun is not really that ambient. It's not really radiating. So the amperage right now will be less than maybe 7. That's a lot. 3.6 is a lot less. So we have a lot more work to do with this panel. We have to dissect it from the back so we could get these wires to all go into the charge controller parallel without the night light displayed, and we could still have a charging capacity that's higher than we currently have. The maximum voltage we have seen is approximately 8 to 10 amps connected to the one terminal, the outer terminal of the solar panel. So right now we're seeing 4.6 and the sun is not really out that much. We're going to take the panel inside and dissect it from the back to see if we could convert it to 312-volt panel parallel. Right now we have it in series with parallel connection. Inside the panel it's still connected in series, but the connection are now made parallel to the charge controller. But that doesn't mean that our circuit to the charge controller is parallel, because the panel is still remain in series. It has to be dissected from the back where the cells are on the bus bar for it to truly become 3 12-volt panel. The reason this diode had to be removed from the bus bar circuit is to take the solar panel out of series circuit. That's one reason why. Another reason why is so that the panel can be split in two, whereas this side may become a 300 watt, a 12 volt, and that side may become a 200 watt, a 12 volt, or vice versa. But what's important is that we have taken the panel out of series circuit, and we now have it ready for parallel circuit with 4 sets of wire, 2 positive and 2 negative. With the center diode disconnected and removed from its port, we're only using the 2 outer ones and experiencing the same problem. Right now we should be getting 10.6 amp at battery volt, but when we try to connect that side of these 2 wire into a different charge controller, it causes problems with the other one, which makes us believe or have evidence to say that the solar panel is still in series with those 2 positive and negative connections. So we have to go back and remove those 2 connection and its diode and test different variety of the pins to see what voltage we could get out of series, so we could have 2 or 3 panels in this one panel connected to the charge controller. Again, it's early in the morning, approximately 8:30. Have the solar panel hooked up on the back of the pickup truck. Have these 2 wires, this one here and that one there, connecting to the diode on that side. So those 2 wires comes up here, go around into this loop, into the charge controller, and we want to take a look at, see what amp we're getting right now. So we're at 14.2 volts on the battery. And we're looking at 4.3 amps. This is better than yesterday. Let's wait for the middle of the day to see what kind of amperage those 2 wires will give us. Then we're going to connect these 2 from this side. That's the small side of the panel. Most likely might be a 100 watt. And this side might be a 400 watt. So this 100 watt side comes down right there. And we have the wires waiting here with the 2 ends here to join with the positive and negative on this set of wires for bringing the complete panel into power with the charge controller. So at 12 o'clock, 11 o'clock, we're going to take another reading to see what the amperage is. So that's 4.2 on the large side of the panel. That's between that right wire and the left wire. Approximately the same time, I have this this is probably a 75 watt 12 volt bulb that you use in the headlight. I have it connected to the battery to create a drain. So I don't have the panel connected right now, but what you see here is I have the 2 negative for both negative on the solar panel connected into the solar charger. So this is the one for the large side, and we can see we're getting 4.8 amps. Now I want to take this one here and just touch it into here to see if the amp goes up from 4.9 amps. So we can see it jump to 9.6 when I connect this wire here. Now let's go back and see again. So we have all the panels connected. And remember, we have taken the panels out of series. So now we could run both of them on the same charge controller. We'll lead for the amp 9.7, disconnect 4.9. So with the large panel at 9 o'clock in the morning, we're getting 4.9. When we attach the small panel to it, we could see approximately 9 to 10 amps at 9 in the morning. So this was the amperage that we were getting from the panel. When you see 9.7, that's with all the panels connected out of series in. So before, when we had the panel with 2 wires at 36 volt 500 watts, we were only getting a maximum of 10 amps at midday. So we're going to wait until midday, 12 o'clock, when the sun is high and rise, and we're going to connect these 2 wires again, the one that I'm holding on here and the one that's in the port down here, and we're going to see if we get a higher amperage reading. Until then, we're going to disconnect the solar panel and let the light bulb create a drain on the battery, so the charge controller will be able to charge the battery so we could see a true amperage. Let's take another look at the voltage reading from the panel that's coming from the 2 wires that will be for the largest portion of the panel. So there we have all our wires connected up there, and it's into the panel. Right now we're getting approximately 10.6 amps. This is the kind of reading we were getting when we had the panel connected in series with a positive and negative. That means the panel was in series to approximately 36 volts or 42 volts. Now we have broken the series circuit and create 2 parallel circuit in the one panel. So this side is approximately, we would say, 400 watts, and the other side, which is this wire, the sun is out right now, you can see the shadow out of the clouds. We're getting 10.4 amps. So I just want to touch this here so we can see what we're getting at 10 a.m. Now this panel is a half cut, so that's 20 amps. That's excellent. So we have doubled the efficiency of the panel by splitting it in half, turning it parallel, instead of maintaining a series connection like originally from the manufacturer. Now we have to go and fit all those connectors back together so they do not become loose and corrosive or loss of connection. So when we take a look at this panel, you can see it's a half cut and it's 6 strings. The manufacturer is Trina Solar, and most of the panel like this, 500, 600 watt, is of this design. It has this thick buzz bar in the middle. This is what you're going to need to mess with, especially the middle one, to make the panel become parallel, so you could segregate the panel. This side will become a 150 watt and this side will become a 350 watt. Let's take a look at the most difficult part in converting this half cut solar panel into 2. So you're going to need to remove this center connector, this plastic. You can see it's just glued up there. You could take a knife. Once you get the diode out of there, you're going to need a solder gun to heat up the end of the diode for releasing these little terminals, these buzz bar that comes from the panel. Once that's released and the diode is out, you'll take a knife and just go around the edge, cutting the silicone to remove this. The reason we need to remove this is because we have to cut this buzz bar right here. If you look at it real good, you can see that's the canvas, that's the plastic. This is approximately 2 to 3 millimeter thick, so you're going to need to really get at it. So this is the buzz bar right here that was connected to this one here. So we cut it to take the panel out of series, and we're going to fold this back. We're not going to use this. It's going to be clipped off. It's going to be clipped off, and we're going to use this center one with this one on the outside, eliminating this one on the inside. So we're going to have to replace our diode for this end, which is going to work with this end. Now the diode is a one-way gateway for the current to flow. It only flows one way, not the other way. So here I have a diode already set up. It's going to be placed in there, and it's going to be welded from the back where the bus bar could be soldered to the terminals of the diode. So you must make sure you check the current flow, making sure it flows in the right direction. Let's take a look at the front of the panel so you can see what has been done here. This is the most important part. You really don't need to remove the diode from this port and this port. It's just this one you need to remove the diode from, because you need to gain access to the panel bus bar for cutting it. Let's take a look at the front of this location here, see what has been done. Here we are in the front of the panel of that same location. So this is where we had to cut for the bus bar to be disconnected from this strip here. So this bus bar was going right across, and it connect with this one here at a cross. It just together. So we had to separate this end. So this side of the panel will have a positive and negative here, and over this side we'll have a positive and negative here. But this is the part where you have to cut for segregating the panel into two. So that will be right there. We cut the bus bar. See there? So it's separated from this side. It's been cut right there. So this part does not touch over here. Let's take a final look at our connection. You're going to need to remove this diode. When you remove it, you have two bus bar connected to the two ends. So you're going to have to clip the one on the right, cut it out as flat as you can to the surface so it does not come in contact with the bus bar. You're going to weld the one on this side, the bus bar on the other side, to this end of the diode, and your cable, your positive cable, will come out of here. You have to make sure your diode is facing the right direction, because remember, it's a gateway for current. It only could flow one way. On the bottom here, you can see we had two terminals here, but we made three since we cut the bus bar on the panel and folded back to segregate the panel in two. This is where it's done. So once that is folded back, it's going to be clipped short, and the plastic could be rolled back for sealing purposes. It's going to leave two wires, two terminal. So you're going to connect to the one on the left. The one on the right will be deleted, obsolete. This could be cut and covered with this connection when we place it over there. This is the best silicone to use. It's high temperature. It's for automotive use. It's most extreme. And it's also an adhesive. You just have to allow it to dry. Once we get that done, we're going to go down here. So here we did not really need to remove the diode. You simply need to attach another wire on this side, because that side will already have a positive for you, so you need to attach a negative. So this don't need any removal, and that's it. It's time to extend this PVC plastic rack that I have for these two existing. Each one of these is 300 watts at 12 volt, but I'm pretty sure the camera can't catch it. If it does, you can see little fine lines of cracks in the panel running across the cell. Well, this is a panel that's giving us a low voltage on one of the charge control panel. We're going to keep it in position because we're going to get ready to add a 500-watt panel on that PVC support attached to this crown at the peak of the roof, where these two half are connected on. So we can see the same thing happening here. You can see little fine lines, cracks. So this panel is approximately, these two panels are approximately 6 years old. And this one here, and the other one on the other side, you can see I have little cracks in it also, scratches below. Don't know what the cause is of that. That one and this one on the outside here are approximately 5 years old. So I'm getting ready to add that other panel up there. You can see this is truly an off-grid house, and it's not something attached to a community or electric poles. So let's attach this frame up here to these T and place the panel with its wire, connect to the charge controller to see the performance we are going to receive. Now, the only reason the panel is placed here and not down there or over here is because in the early morning, that's where the sun rises. So we need the sunlight energy to boost the battery early in the morning. In the afternoon, one could be placed back here, but the sunlight in the afternoon, in the evening, is not that radiant. So maybe later on we'll focus on the rear. Using 2-inch PVC pipe plumbed into the existing solar panel support, the PVC pipe is filled with sand to create a weight against the roof, preventing wind from blowing the structure away. It also prevents water from leaking into the house by using fasteners or screw to hold on the solar panel to the structure. This is the best method.